Hello and welcome to my ad hoc explanation of the generalized linear mixed model in SPSS. So generalized linear mixed model here means that we have repeated measures. And we have this very big table here with lots of data. And we have subjects, we have various independent factors, and then we have a dependent variable or several dependent variables. Now we can only do one dependent variable at a time, and we can only have a repeated measure at a time, one factor. And the factor for the repeated measures is this factor called special frequency. And you can see there are 7 different values, and each one of the subjects here, which is a cell, animal phi cluster, that's a cell, that's a neuron, was tested for each one of those special frequencies, and we got some kind of dependent variable. So the DSI had a value for it, the OSI had a value for it, the evoked rate had a value for it for each one of those 7, for every cell. Okay, so the cells were also part of animals, and each animal is some sort of covariate or random factor. But I'm going to skip this part for now and just concentrate on the main factors. So we have, first of all, the subjects. So let's go here, generalized linear model, mixed model, sorry here, generalized linear mixed model. And let's start at the beginning. So the subjects were here. Animal phi cluster, that's the neurons. Okay, put them to the right. Okay, go to the next one. Target. Here you have to choose and put your dependent variable. For example, it could be, most of these could be dependent variables. There are measures made. You know, this one, for example, is potential. But for now, I picked up this one. Okay, all of them are interesting. So you put that there, and then you have to decide whether the distribution of your dependent variable is normal, in which case we have a linear model, and if it is normally distributed, there's no even reason why we should be using this this method, or whether we have a gamma regression or some other distribution. Of all these options, the closest one in my case, the closest to the distribution of the data, is this gamma regression. So I'm going to pick that one. And then we go to the fixed effects. I've already picked up these ones. And these were on the left, and I put them on the right. So animal genotype, anesthesia, and layer. You can see layer, animal genotype, and anesthesia is filled. Okay, the build options I haven't changed. It's about the confidence interval and so on. I haven't changed those. And finally, here, under estimated means, you have to click on this so you get an output with the means and standard errors. Otherwise, you don't get that, and you cannot write a proper report if you don't know what the mean and standard error is for, you know, the groups and variables. So click on Run, and here's the summary of the data. So probability distribution, we say that's gamma as a log link, and the function. And the fixed effects, those 3, animal genotype, anesthesia, and layer, 2 of them are significant. The anesthesia and layer. And here, the boldness of these lines shows which effects were the strongest. So layer was stronger than anesthesia was stronger than animal genotype. Then over here we have the levels, individual levels of the 3 factors. So we have the 2 levels of genotype, and you only have one comparison. It applies to the other one, and we get a coefficient and a standard error or whatever, and then the significance is here, 0.266. For the anesthesia, the significance is 0.003, so that's highly significant. And for the layers, it's here, and 2 of the layers. Not only is the layer as a factor significant, but because we have several levels now. The levels is said, it's like a postcode test. It tells you which levels show the biggest differences for anesthesia versus awake, because the genotype was not significant, so it's not doing that. Yeah, it's only comparing anesthesia versus awake, which was the significant difference here. Yeah, and so it finds that layer 3 and layer 4 were significantly different than layer 5. Layer 5 is, sorry, layer 6. Layer 6 is taken as a standard for some reason. And then layer 4 and layer 3 and layer 4 were different. Okay, and then we get some graphical output, which gives you the mean and standard error for each, for those fixed effects that were significant fixed effects. So here is the OSI by layer and the OSI by anesthesia, but genotype was not significant as a factor. We do not have significant fixed effects, so it's not included. Okay, and you see layer 5 and layer 6 are very similar, but layer 4 and layer 3 deviate so significantly. And these two here are significant. Now, so far we haven't seen anywhere the mean values being pointed out. We don't have any mean values, and we don't have the standard error of the mean, or the median rather, because it's a non-normal distribution. So we're going to get those down here. I assume this is the median and not the mean. I assume. We have what I assume is the median. It could be the mean. I'm not an expert in this. And then we have the standard error. And so for knockouts, the mean OSI was 0.462. For wild types, it was this one. These are the standard errors. If you remember, this was not a significant effect. And here are the two values with the standard errors, and this is not significant. However, anesthesia was significant. And so these are the two values for anesthetized and awake, the OSI of the anesthetized and the OSI of the awake. The standard error of the two. And here are the two means, presumably medians. I can't be 100% sure. And then over here we have the standard errors. Maybe it's estimated means like the median, but somehow it's estimated as a mean, so we can have a standard error. I think it's something like that. And in any case, so here are the estimates of the layers, and again we have a kind of estimated mean and a standard error value, so it can be plotted in this way for kind of graphical comparison. But you also have the means, so they can be reported, the estimated means. So that was the end of my presentation. The best I understand, to the best of my understanding of the SPSS linear, generalized linear mixed model analysis.